In this proof, we show by induction that the sum of the first n powers of r is equal to 1 minus r to the n plus 1 over 1 minus r. We define the set S to be the set of all natural numbers for which the proposition is true. As with all inductive proofs, we begin by establishing the basis for induction. And here we choose n equals 1. This expression with n equals 1 is 1 plus r. Multiply this by 1 minus r over 1 minus r. Simplify the top to get 1 minus r squared over 1 minus r, which is exactly this expression with n equals 1. So we've proven that the proposition is true for 1, hence 1 is an element of the set S. Now we perform the inductive step. There's a common misconception about induction that you're assuming to be true that which you are trying to prove. That is not the case. We're trying to prove that the proposition is true for all natural numbers. We're assuming that it's true for just one natural number. We don't specify the natural number, we leave it as m, but that is one fixed natural number. We then use that to show that it's true for n plus 1. Now the strategy is to write the left-hand side with n equals n plus 1 and then transform this expression into the right-hand side with n equals n plus 1, using the inductive hypothesis along the way. So if we rewrite this as the sum of the first m powers of r plus r to the n plus 1, now this expression is in the form of the inductive hypothesis. We can then use the inductive hypothesis to substitute for this expression. And that's what we do here. Now we want to combine these two, so we need common denominator. So multiply this by 1 minus r over 1 minus r. Then distributing r to the n plus 1, we get r to the n plus 1 minus r to the n plus 2 over 1 minus r. Now that we have a common denominator, we can combine these two into one fraction. Notice we have an easy cancellation here. We have negative r to the n plus 1 plus r to the n plus 1. Those two cancel, and we're left with 1 minus r to the n plus 2 over 1 minus r, which is exactly this expression with n equals n plus 1. Thus we have shown if the proposition is true for m, that implies that the proposition is true for n plus 1. Therefore, the set S is indeed the set of all natural numbers. Because since we established the basis for induction at 1, the fact that the proposition is true for 1 implies that it's true for n equals 2. The fact that the proposition is true for n equals 2 implies that it's true for n equals 3, and so on throughout all the natural numbers. That is the beauty of induction.